Mining U308, conversion UF6, enrichment UF6, fabrication.
Over 50% of uranium deposits today use the in situ method of mining. Using this method, water wells are drilled into the uranium ore body and groundwater is circulated with oxygen. When oxygen is added to the water, it rusts the rock. Rusting uranium changes its color from ash gray to various bright shades of yellow. This yellow oxidized uranium is soluble and is brought to the surface and extracted from the water through a treatment process. In conventional uranium mines, the rock is extracted from the earth, either in tunnels underground mined with drill bits studded with tungsten carbide, or for more shallow deposits, dug up from the surface through pits created by excavators, known as open pit mining.
The uranium ore lies beneath a bed of water-saturated sandstone. To reach it, they use drill bits studded with tungsten carbide buttons. These first holes are for pipes that will pull heat out of the ground and freeze it around the ore. They configure the pipes so they surround the ore deposit. These freeze pipes will stabilize the ground, and they'll also turn high-pressure groundwater to ice so it won't interfere with the actual mining. As this animation shows, the drill pulls the reamer up the pilot hole, widening it, and the broken ore falls into what's known as an extraction chamber. Here, a tram operated by remote control scoops up the rock. The tram now empties the ore into a chute. Cameras follow the rock's journey to the next station. Then, from a control room, an operator manipulates a hydraulic hammer to smash the ore to bits. Trucks transport the uranium ore slurry to a mill. Acid dissolves the uranium, but not the rest of the rock. It settles to the bottom of these tanks. The uranium acid solution flows forward, leaving the unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium. Then they roast it at 850 degrees Celsius. They stack the drums in a warehouse to await shipment to the next processing plant.
Centrifuge. Uranium hexafluoride gas is fed into the rotating cylinder and spun at a high speed. This is what splits the molecules. The heavier U-238 molecules collect on the outside of the cylinder, and the light U-235 molecules set closer to the middle. The gas that's slightly depleted of U-235 is sent back to previous stages, and the gas that's slightly enriched is fed to the next stage. This is done through a cascade, which is made up of hundreds or thousands of centrifuges, until it creates a gas that's highly enriched in U-235.
Uranium dioxide, the chemical form required for nuclear fuel. Spinning the uranium dioxide mixes the different-sized particles to make it a more homogeneous blend. The chemical processing has also caused the uranium to change color again. It's now a fine black powder. Using several tons of pressure, tools shape the uranium dioxide into pellets. A revolving wheel with protrusions guides the pellets into a channel conveyor. The conveyor takes the pellets into a furnace. Over 24 hours, the heat removes pores in the pellets. The pellets shrink, increasing the density of the uranium. The particles fuse together and harden into a ceramic. Here is a pellet before and after baking. A robot arm now loads the pellets onto a tray and levels them. A conveyor moves the tray forward. Ahead, another robot places zirconium fuel tubes on a rack. Zirconium is a metal that's highly resistant to both heat and corrosion, but neutrons will pass freely through it during the fission reaction. The rack of tubes meets up with the tray of incoming pellets. A robotic loader pushes the stack of 30 pellets into the tube. Another robot delivers the rods one at a time to an automated welder that caps the ends. The next robot retrieves the completed uranium fuel rod and transfers it to an assembly fixture. It arranges a total of 37 rods in an upright position within the fixture. After the rods have been welded and the bundle capped at both ends, a robot transfers it to a scale. This weigh-in confirms that there is the correct amount of uranium in the bundle. Prior to burnup in a reactor, the amount of radioactivity emitted by nuclear fuel bundles is very low, and they're safe to handle as workers prepare them for shipping. They're now on their way to the power plant,